So this set of notes is going to look at some of the instruction set architecture features we've been looking at in other sections and compare the implementations and historical design perspectives of a bunch of different assembly languages that you may or may not be familiar with. I'm not assuming any familiarity with any of these languages, but there are other videos where you can sort of learn about ARM or MIPS or LC3 or RISC-V. I've got some x86 sprinkled in here as well. So we've got, these five: RISC-V, MIPS, ARM, x86, and LC3. And the idea is to look at the different implementations of design perspectives to see where these things came from, which ones are better, and why they are the way they are, why some are the same and some are different. So we're going to look at a whole mess of different design features of an instruction set architecture. We're going to look at instruction formats, register decisions, data formats, addressing modes, computation options, control branch, exceptions, privileges, extensibility, all these kind of things. And the key here to recognize is that there are bits of a computer design that are not related to the instruction set architecture. So pipelining, for example, any of these machines could be done in a single cycle or in a multi-bus or pipelined, but that's not a feature of the instruction set architecture. In fact, it should be hidden, right? The same code should be able to run on a 3-stage pipeline or a 12-stage pipeline, just with different branch hazard considerations that the compiler and the assembler will have to agree to how to handle. Memory hierarchy, the same thing. How many levels of cache should be separated from this stuff and can be implemented independently. Multi-programming, microprogramming, multiprocessing, all of these are not features of the instruction set architecture, but instead are features of the implementation in hardware of that architecture. So a few themes will emerge here: reduced instruction set versus complex instruction set, regularization versus specialization, right? Trying to make everything look the same as opposed to make everything specialized. And there's a quote in the Patterson and Hennessy book that says, make the common case fast. So the regularization is to try to make as much look like itself so that you can make those processes a lot faster. And then we'll look at whether or not the machine maintains a state of information or not. And then we'll look at, common cases and exceptions. So first, we're going to look at the instruction formats in general. We've got a couple of different directions that these ISAs go. Orthogonality is a phrase that is used in these design decisions that talk about whether the instructions and the data can interact with each other, or whether separate instructions and separate data are always specialized. In early days of assembly language design, you had a lot of specialization. You would do different kinds of data instructions and different kinds of memory access and stuff like that. But in the modern implementation, they try to make things as similar as possible so that they can be fast. So orthogonal just means that any operation can be used with any register and any addressing mode. And that's mostly true for most of the modern languages, but there are, of course, exceptions. The other question about instruction formats is how many operands. You always have an opcode and then some number of operands that will tell you where to find the information you're looking for. Modern assembly languages typically have 3 operands, right? 2 sources and a destination. Although there are some that have fewer if you're doing slightly different things, but that's the general structure. Some earlier assembly languages only have 2 operands, and they treat they treat one of the operands as both source and destination. So A equals A plus B, you'd only have to say A and B, and the machine would decide that this one is the destination as well as the source. That is more efficient in terms of the size of the instructions, but it also restricts the functionality sometimes. And so that's why modern languages are typically 3 operands and then different formats depending on what you're doing. The instruction size, many of the languages we're talking about in these series all have the same instruction size, and we sort of take that for granted, that instructions are 32 bits long, just like data is 32 bits long. Everything is 32 bits long. That's a feature of orthogonality and was not necessarily true. In the early days of machine language, you had different instruction sizes depending on the function, and we even see that today with x86-64 inherited the variable instruction length, and some of the compressed formats that we'll talk about in a second have also inherited variable instruction length. Compressed formats are this idea of a 32-bit instruction is the regular size of instruction, but maybe we find a very compact, like a 16-bit instruction. That way we can make our instruction code very compact, right? Reduce the size significantly, maybe increase the efficiency for embedded applications or other kind of structures. And so the idea of a sort of a smaller version of the same format is a thing that we see sometimes as well. In fact, these are the compressed formats that we start to see these days. ARM has a version called Thumb. ARM is 32 bits, Thumb is 16 bits. The 32-bit version is fairly clean and nice to sort of, everything is in the same place, more or less, although there are some complexities with the immediate format. Thumb is a little bit more unusual because to fit the same kind of instructions into 16 bits, you have to really constrain stuff. Fewer registers, smaller immediate values. There's a lot of sort of compromises you make to make a smaller instruction length, but you get a lot of benefit because you can fit more code into a smaller place. RISC-V has a 32-bit mode and a 16-bit mode. It also has actually a 64-bit mode that does other different things. And so, again, you want to have some options for a smaller instruction, a tighter instruction set, if you don't need as complicated a processor, and you can get away with specifying fewer things for the instruction, then you can build some efficiencies in terms of not just the instruction size, but the speed of the processor as well. x86 did not have compressed formats, but it did have this idea of variable instruction length. So some instructions are only 8 bits long, some are 16, some are 32, depending on what the instruction is doing and how many operands of what kind are needed. So fewer and smaller operands means fewer registers available. These are all the considerations for compressed formats and different sizes of instructions. Because to specify a register, of course, you have to specify the address of the register in the register file. If there's 32 registers, you need 5 bits per register, right? So if you want to have a smaller instruction, maybe you only have 16 registers. ARM only has 16 registers, for example. You would also build in more implied or inherent operations, as we'll look at later on. And again, you'd have a smaller range of immediate values. So why do you do this? Well, again, code density is one of the big considerations. Smaller executable files, less memory usage. It's interesting to note that theoretically, if your code is going from 32 bits per instruction to 16 bits per instruction, you should be able to cut your code size in half. You can't. Usually you can't. And that's a good question, is why can't you just cut your code size in half? Well, because the instructions are less powerful, which means sometimes you need more of them to do the same operation, right? You can bring in more instructions per cache miss, and that can optimize your performance. You can implement simpler, smaller, faster, reduced power machines. So these are the kind of things you might do with compressed formats of instructions. So this is sort of the basics to begin with. In the next video, we're going to look at all the different addressing modes, and then in subsequent videos, we'll look at other considerations when you're making decisions about different ISA features and structures.